Well, welcome to our section on equation solving and modeling. This section is going to be pretty short. I just wanted to go through a couple of example problems in this section to show you how to use two of our one-to-one properties. Our learning target for this lesson is just to be able to use logarithms and exponents to solve actual problems. And some of these in your homework assignment will be word problems, and the ones that I'll have in the video here will just show you kind of the skills of how to deal with the algebraic manipulation to solve those problems. So here we go. Two of the properties that we've actually already been using say this. For any exponential function that we have, as long as we have the bases the same, then we can set the exponents equal. We've been using that already, so that's nothing new. And for logarithmic functions, as long as the log is to the same base, then whatever we're taking the log of, those are equivalent. So let's go ahead and use those two properties to solve some problems. So here's our first problem. This one says 32 times the 1/4 base to the x over 3 power equals 2. And the first thing we want to do is isolate. We're trying to solve for x, so we want to isolate everything else that's not related to x. So divide by 32 on both sides, and that gives us 1/4 to the x divided by 3 power is equal to 1/16. And 1/4 and 1/16, we can get 1/16 to be a power of 4. That would just be 1/4 squared. So if we write it that way, our bases are now the same. And if the bases are the same, then the exponents must be equal. So once we set the exponents equal to each other, we get x over 3 equals 2, and then multiplying both sides by 3, we get x equals 6. In the second example here, this one is a little bit easier. We can just change from logarithmic to exponential form, and that says take our base 2 and raise it to the 5th power, and that would equal x. And 2 to the 5th power is 32. Our third example, the first thing I would do on this one, we could do the same thing where we just change it from logarithmic notation to exponential notation. So 4 to the 1 power is 1 minus x. Subtract 1 from each side and we get negative x is equal to 3. So that means x has to be negative 3. All right, our next example has logarithms on each side. And a couple of different ways you can solve this. I guess the way that I approach this, since we know the sum of two logs is equal to the log of the product, I went ahead and wrote this as the product of two factors. And so once we have that, we have the log, same base, these are both base 10. So we can just set those two things equal, and the 2 that was in front of the log, I changed that to the exponent. Then we can just drop the log notation, and we end up with x minus 2 times x plus 5 is equal to 9. And then using our FOIL for our binomials, multiplying those out, we get x squared minus 3x minus 10, and then I subtracted 9 to give us a 0. And then we can just take our quadratic equation and plug it into the quadratic formula. If you do that, you end up with this value. X is equal to negative 3 plus and minus square root of 85 all over 2. But if you use the negative value, remember we had a couple of rules back in a previous chapter that said you can't take the log of a negative number. That does not exist. And if you use the negative value here of negative square root of 85, that actually gives us a negative log value, and that can't happen. So we need to throw that one out. So the only valid solution that we have for x is the one where it's negative 3 plus the square root of 85 over 2. And if you calculate that on your calculator, that's about 3.110. All right, and another example here. This time we have the logarithm on two sides, but not on the right side, just on one side. And when we're subtracting the logarithms, remember that means it's a quotient. So we could write that as the log of x over x plus 4 to the 1/2 power. And the 1/2 power is just the square root of x. So that's what our logarithm looks like when we do that. Then what we can do is go ahead and write it in exponential notation. So we have, remember this is a common log, the base 10 to the first power equals the thing we have in parentheses. And then I'm going to multiply both sides by the square root of x plus 4. So we get 10 times the square root of x plus 4 is equal to x. And to simplify that, remember we're trying to get x by itself. We need to get rid of the radical, and we've got an x on both sides. So let's just square both sides. And when we do that, we get 100 times x plus 4 is equal to x squared. And then distributing the 100 through the parentheses gives us 100x plus 400 equals x squared. And then if we get all of our terms on one side, we have a quadratic equation that again we can plug into the quadratic formula. And we end up with 103.852. Again, we're going to ignore or throw away the negative value. When you get the negative value for x, we can't have a negative log. So I threw away the negative value from the quadratic formula and only used the positive. So that's one of the things you want to be aware of, is make sure that you check your answer, plug it back into your original equation to make sure that you have valid answers. All right, our last one here says if f of x is equal to 3 log of x minus 1 to the base 4, find the inverse of the function. And remember from a previous chapter, finding the inverse, we're just going to exchange x and y and solve for y. So I wrote this one, y equals 3 log x minus 1 base 4, and then I went ahead and switched those, just switching x and y, and remember our goal is to solve for y. So the first thing we want to do is divide both sides by 3. And then we can go ahead and change from logarithmic to exponential notation. And if I do that, I have 4 as my base. This side will be my exponent, and then I have y minus 1. So now, remember, we're still just trying to solve for y, so I just need to add 1 to both sides. And I get y equals 4 to the x divided by 3 power plus 1. And that is our inverse. So it's not real pretty to look at, but that is what it is, and that is the inverse of the previous function, the log function that we were given. And that'll do it for this lesson. See you next time.